Hello all and welcome to this video where we look at functions, to this video where we look at functions, how they are, what defines a function and how to write them. I guess our learning intention is pretty much that, is to identify if a type of relation is a function and also to write using function notation. So let's jump straight into it and look at what a function is. So a function, as it says here, is a well-behaved relation. Okay. And by well-behaved, it means that for every x value, it could be we're mapping coordinates to something, or we have coordinate pairs, or we could also have a equation. But for every x value in that equation or set of ordered pairs, there is only one corresponding y value. So a way to think of this is a function cannot contain two different ordered pairs where they have the same first coordinate. We can't have 2 and we get a 4 for y, and we also can't have 2 and a -4. If we get this situation, that is not a function, because the same x value can give different y values. So for every x value, it can only give one y value. Now, for a function, the most basic form of functions, we are allowed to have, though, it doesn't matter if different x values go to the same y value. So we can have 2, 3, and we can have 3, 3. That's completely fine. Okay. The x value of 2 maps to 3, that's fine. The x value of 3 maps to 3, that's completely fine. What we're not allowed to have is this 2 mapping to something else. We can't have it map to anything else. So for every x value, can map to only one y value. So keeping this in mind, let's have a look at these certain mapping diagrams below and see if they are functions or not. Looking at this first one, we can see -3 only maps to one number, -2 maps to only one number, -1 maps to only one number, 0 maps to only one number, and +1 maps to only one number. So this is a function. All the x values map to only a single y value. Looking over at our second example here, -3 maps to 1, that's fine, -2. I should put the ones over here. -2 maps to only one value, -1 maps to only one value, 0 maps to only one value, but x value of 1 maps to 0 and 15, so that maps to two values, so that's not a function. The one x value, thinking our domain is our x and our range is our y, our x value of 1 gets mapped to 2, so that is not allowed to be defined as a function. So a function is just a special type of relation. For example 3, down here in the bottom left, -3 maps to -6, so it's mapping to only one number. Okay. -2 is mapping to only one number, so that's fine. -1 is mapping to only one number. 0 is mapping to only one number. 1 is mapping to only one number. Even though they all map to the same number, each of them is only mapping to one number. So that's completely fine. So this is classified as a function. Okay. This fourth example, people miss it when looking at it, but we need to include this 16 down here. There's this 16 here. So -3 maps to one number, so that's fine. -2 maps to a number, -1 maps to a number, 0 maps to a single number, 1 maps to a number, but 16 doesn't map to anything. It's got nothing here. Since it's not mapping to anything, this is technically not a function. Okay? Every number needs to map to one and only one number. Every x value needs to get mapped to only one y value. So that's not a function. So hopefully those mapping diagrams help a bit. But another way to think of it is visually. Okay? And the way that we can visually check if a relation is a function is using what's called the vertical line test. Okay? If we draw a vertical line test anywhere on the graph, so just a line going straight up and down, if it only crosses once, well, that means that every x value matches to only one y value. So let's have a quick look at this first function. We can see, draw a line down here. My x value maps to one y value. my X value maps to one Y value. My X value maps to one Y value. X maps to one Y. X value maps to one Y. And we can see it doesn't matter where we draw our vertical line, it only crosses once. It only crosses our function once. So this would be considered a function. Okay. So for that, and we'll come back to talking about the maximal domain and range in a second. Okay. Now, this second example, let's draw a vertical line in. Okay. Here, we can see that my X value of, say, negative 1.5 can map to up there, but it can also map to down here. Okay. So my X equals negative, let me write this properly. If X is equal to negative 1.5, I can see my Y value is equal to about, let's say 1.5 as well, and it could also equal to Y is equal to negative 1.5. So for the one X value, I'm getting two different Y values. So this is considered not a function because it is not passing the vertical line test. I've drawn a vertical line in, it crosses my function twice. So that is no good. Let's go back now and look at maximal domain. So maximal domain is what are the X values that make this work? Well, in this case, looking along my X-axis, I can put in any number. I could put in positive 200 because we're assuming this line goes on and on and on. Okay, I could put in positive 200. I can put in a 2. I can put in a negative 4. I can put in any number. So my domain for this, okay, is equal to any real number. What's the range? Well, the range is any of the Y values that we get out. So what are the Y values that we can see that we're getting out of this equation? Well, our Y values are from negative 1 upwards. So my range would be equal to when Y is greater than or equal to 1. We could also write that as that way. We could also write it as negative 1 up to positive infinity. Any of those would work. For this second example, what are the allowable X values? Well, X can be anywhere between negative 2 and up to positive 2, and same with our range. Since it's centered at the origin, we can see our Y values are anywhere from negative 2 up to positive 2. Okay. So that's what a function is. It needs to be able to pass the vertical line test. Every X value maps to 1 and only one Y value. Now, to distinguish between a function and a relation, they are written in different notation. Okay. Functions are normally named. They're actually given a name, and we usually use a lowercase letter. Generally, F, G, or H are the ones that are normally used. And the element Y, because we need to think really we're taking some X coordinate, doing something to it, and we're getting a Y value. Okay, so the elements, we're taking element X as doing something, getting element Y out. So the element Y is called the image of X under F. Okay, so we're taking some element X, doing the function F to it, coming across, and we're getting some new element called Y, which is the image of X under F. So think visually, I'm taking some X values, changing how they look, and I'm getting some new image given by the function F, and then we call the element X the pre-image of Y. Yeah, that's just some really funky maths way of sort of talking about functions. since the y values obtained is a function of the x value, so we start with the x, do something to it, we use the notation f of x, okay, or the f bracket then x, and we read that as I just said, we read it called f of x. We're doing the function f to x, and we put that instead of y. So instead of writing y equals 2x plus 1, we actually write it, we give it some name. So in this case, we've given it f, and we're working with the variable x, so the x goes in the brackets. So the function of the starting variable x is equal to 2x plus 1. And then if we write f of 2, that means, well, let's make x equal to 2 and find what the y value is. So if we've done that here, we've made x equal to 2, and we subbed it in, and we get 5. If we let x equal to -4, we're going to get 2 by -4 plus 1, so we get -8 plus 1, so that's -7. We can also sub in other letters in place of it, so we're still just putting a in for where x is, so we get 2, put our a in plus 1, so we get 2a plus 1. So it looks like identical, but just with an a instead of an x. Rightio. So that's the basic sort of naming of it. Now to get the full notation, we have to write it with this. This is the name we give the function. We then put our ... so we're pretty much saying condition. So we've got a function named ff. We put our 2 dots. We then put our domain. Okay. You can write it in set notation or interval notation. But have a look in the textbook and you'll see what trends there are for that. We then put this arrow sort of showing that we're mapping this domain into this new thing. And this is where people get confused, is this new thing called Codomate. Now, almost always, the codomain is just real numbers. Okay? Because the codomain could be defined as what are the possible values of y that we could get for all types of this function. And what I mean by all types of this function? Well, let's just say if we started with x squared. Okay? Well, what are all the types of sort of the x squared shape? Well, we can have the x squared, which looks like that. We could then have x squared minus 5, which looks like that. We could have x squared instead plus 5, which looks like that. We could have x squared minus 1 million if we really wanted to. Okay? With the turning point way down here at -1 million. Okay? So that's what I mean by types is, if we think of the general shape, what are the different ways it can appear? Well, we can move it up and down, we can move it left and right. Where can it exist? And it pretty much means that almost always, depending on how we change this by just putting a constant at the end, moving it up and down, the possible y values we could get are everything, all real numbers. All real numbers. So almost always you're going to put R here. I don't think I've ever actually come across a question unless you're actually changing the type of numbers that we're putting in the domain, because most of the time the domain we're restricting to a set of numbers that might be between like 2 and 4. We still put real there, but sometimes the only time where this is not going to be real for the codomain would be if we instead change our domain to be something like we're only allowing natural numbers. So I'm only allowing whole positive integers. Well, that means my codomain, depending on what this function is here, could also possibly only ever be natural numbers, depending on what this type of expression is here, if it's going to actually give us whole numbers or decimals. But yeah, effectively stick an R here after the arrow. And then we have f of x. Again, we have to write it out because what's the name of our function, what variable are we dealing with, and then we actually put in what the equation or expression is. So that's a lot of talking. Let's have a look at some examples. Rewrite each of the following relations using function notation. So we're dealing with variables x and y, where y is equal to negative 2x plus 5, and x needs to be greater than 0. So this is our domain. Okay. Now we get to call it whatever name we want. Usually we're going to call functions f. So let's call it f. So we're going to call it f. Okay. What's our domain? Well, we were given our domain. X needs to be greater than 0, so or equal to 0. So we could write that just as x greater than 0 is one way we can do it. And what's that going to map to? Well, this is a linear equation, so a linear equation, it's allowable y values if we had no restriction on it. Because y values can be positive to negative infinity. So we just get all real numbers, comma, f of x, because that's the variable we're dealing with, is now going to be equal to negative 2x plus 5. Make that a little bit neater. This second one, we have y is equal to 1 on x minus 2 all squared, where x is not allowed to be equal to 2, because if we put a positive 2 in there, we get a 0 in the denominator, and we can't divide by 0. So again, we are told our domain in this case. So we get, let's call it, instead of f, we'll call it g. Call this one g. So g, what's our domain? Well, our domain, how do we write x not equal to 2? And we want to try and use this using set notation. Well, that's all real numbers except 2. And that's going to map to, and again, we just pretty much put all real numbers. And then we've called it g, so we've got g of x is equal to 1 on x minus 2 all squared. Okay. So you're going to try to always write our domain using set notation rather than interval notation, but sometimes interval is pretty clear. How could we write x greater than or equal to 0 using set notation? Well, that's real positive and 0. So this u means union. So that's the other way we could write this, is real positive and 0. It's mapped to all real numbers, where f of x is equal to negative 2x plus 5. So the long and the short of it is, it's just a tedious way of writing equations. But like I said at the very start of the whole topic, in the very first video, this will be really helpful come later in some later topics that we covered this year and especially next year in year 12, because depending on what we do here, this will be a function or not. It may pass the one-to-one, that vertical line test, or it may not, and then it means we can do some shortcuts. The very last thing to deal with is how we can do this on, do some function stuff on CAS, and in particular find minimum and maximums. It's a really common question in exams. Find the minimum, find the maximum, especially in the tech active. And how can we do this? So there's a full written out instructions there, but I'll also show you how to do it using this example down the bottom. Find the range of f, where our domain is from -3 up to 6. Codomain is real for the equation f of x equals x squared minus 2x plus 1. What's the minimum and maximum values of that? Well, let's bring in the calculator, go into our main window. Let me clear year 12 stuff. Okay. That's a really good thing to do at the start if you've been doing, when, as I'm going to show you, when to store some things, is clear all the variables and clear everything off your main screen. So the first thing, and this will be something I'll harp on throughout the whole year, the very first thing you want to do is store the equation. Just not write it out, but we actually want to store it. And the way we do that is using what's called define. we're going to define or store the equation, which happens to be in Math 3. So define, and in this case, we were told our equation was called f of x is equal to x all squared minus 2x plus 1. Okay, and we were given a domain, we were given some restrictions, so we want to include that because that is technically what this equation is. It's not the whole thing, it's not all of x squared minus 2x plus 1, it's x squared minus 2x plus 1 for x being between -3 and 6. Now how do we do that is we need to use this, I go back to the slides quickly, we need to use this vertical up and down line. You can see it put in here. That means given. Ooh. And that is here in Math 3 on the far right hand side, given, and then we can put in our restriction. So we need to be what was it, negative 3 x up to 6. Okay, and then I hit enter, and that's going to store the function. Okay. Now, why do we want to store the function? May as well go over this now really. Oh no, we've gone long. But really quickly is I could find what the whole function is equal to when x is equal to 2 by just typing f of 2 because I've stored it. If I go to graphing, so this graph picture up here at the top right, bring that up, and I want to go to the equations, and now I can just put f of x in, click next to it, click the graph button again. That's going to graph it, and I need to zoom out. Let's zoom out. Okay, and there we can see, and we see the endpoints at the far left and the far right. So we want to find the actual minimum and the maximum. That can be pretty easily done by using this analysis gsolve button, and we can see min and max. Min, it gives it to me when x is equal to 1 and y is equal to 0, and it also labels the coordinate for me. So straight away, if I come back here, the min is at 1, 0. And then if we go analysis gsolve and I want to find the max, not found. Oh, so that's not finding a local maximum. So it's what the gsolve is trying to find is a turning point. So let's try fmax. Not found. Okay. But we can quite clearly see that that is going to be over here when at the far right of it, which was when x equals 6. So if we go back to our main window, because we stored the equation, we can now just go f. I want to know what the function is equal to when x equals 6, and it gives me 25. So my max is at 6, 25. That's how we can find the min and max and store a function with a domain as well on your CAS. You can not do the define and just type out that whole thing in the graphing section. You can do that as it's shown here. You could type it out in full, but it's much better to store it first because generally you're going to have to do multiple things with it. Find values, find mins, find maximums, so may as well store it. Makes life easier. That's it for exercise 5C. Sorry I've gone over again by 4 minutes, but just wanted to try and be clear. This is one of those things where it's just repetition. There's plenty of examples in the textbook too that you can get a bit of an idea from of the trends and how we can write different domains in particular. If you have any questions, put them in the comments below or in Google Classroom, or feel free to send me an email. Thanks and see ya.